Okay, this is the debrief on the test. The first few problems said work these easy integrals. Be careful and check your answers. Do you like the capital C there? So check your answers. This first one is obviously integration by parts. Theta, the derivative, and the derivative. Sine of 3 theta. The antiderivative, now remember the antiderivative of sine is a negative cosine. Angle stays the same, need a 3 in there. And the antiderivative cosine is a sine. Oops, 3 theta. Angle stays the same. So this is going to be -9. Here's your plus minus. So it looks like the answer is -3 theta. This would be a positive plus 9 sine of 3 theta plus a constant. Now that was a tedious problem, I guess. Let's look at the other ones. Oh, so this is like super easy, right? This is a u to the n. So we have the 3x plus 1 to the 4th. We need a 3 in there and a 1/3 here. So answer is 1/3 3x plus 1 to the 5th over 5. Or if you want, you can do 3x plus 1 to the 5th over 15 plus a constant. This is basic trig, right? We can pull the 2 out. The derivative of tangent is secant squared. And so the integral of secant squared is tangent, but we need to have the correct du in there. So it looks like we get 2/3 tangent of 3t plus your constant. Number 4. At first glance, this looks a little strange, but in fact, it is an arctan. Remember, the arctan rule looks like this, where we have 1 over a squared plus u squared. So I think of this as, I pull the 6 out, and I have the 1, 5 plus x squared dx. So the antiderivative, there's the 6. We have to have a on the bottom. This is a squared, so this would be the square root of 5. Arctangent of u, which is x, over a, which is square root of 5. So a little tricky. This one's a whole lot easier, I think. We've got 2x minus 1 to the minus 1/2. We can pull the 4 out. We have to put in a 2 and compensate, right? So final answer, it looks like we have 2x minus 1. Got to raise the power up by 1, divide by the new power. Dividing by 1/2 is multiplying by 2. So 4, 2x minus 1 to the 1/2 plus c. Number 6. Looks like a circumference of a circle. Well, let's see. Pull the constant out. 2 pi. I know r is the variable because that's the differential. So we get 2 pi r squared over 2. Well, that simplifies as pi r squared, right? The 2's cancel, plus a constant. Interesting. The integral, the antiderivative of a circumference is an area. This one, I think, was in the problem set. This is the natural log of x to the 6th times 1 over x dx. So there's your u, there's your du. Natural log of x to the 7th over 7. Typically written this way. Don't forget the constant at the end. Number 8. This one was also in the book. This one is a partial fraction, so you have to go off to the side and write this as a over x plus 5 and b over x minus 5. It doesn't matter which one goes first. And then just make some notes. If x, well, first of all, let's get the characteristic equation, Joe. So multiply through by the common denominator, and we get 25 is a times x minus 5 and b times x plus 5. Okay, so that's going from there to there. Let me get this out of the way. If x is 5, we get 25, that's an arrow, is equal to, this goes out, and so we get 10b. So b is 5/2, and so when we're going up here, I erased my partial fractions. I had the b over top of the x minus 5, right? I had the b over top of this. So this is 5 halves times 1 over x minus 5. And then if a is negative 5, sorry, if x is negative 5, it's been a long day, then I get 25 is x is negative 5, so we get negative 10a. So a is negative 5 halves. So this would be negative 5 halves. And again, the a was over top of this. I'm pretty sure. 1 over x plus 5. I shouldn't have erased it, obviously. Okay, so that's what we're integrating. Let me just double check real quick. We had 25, x squared minus 25. And I think I had a over x plus 5 and b over x minus 5. Characteristic equation, yeah, that's right. So the a is over the x plus 5. And a worked out to be, there we go. Okay, we got it. So now here's the antiderivative. 5 halves, natural log, absolute x minus 5, minus 5 halves, natural log, absolute x plus 5, plus a constant. You can combine those if you want. You don't have to. This is the one that we did in class. Derek helped us out with that, maybe. So the integral of e to the 3x sine x dx. If we put the e to the 3x here, the derivative is 3e to the 3x, and the derivative of that is 9e to the 3x. We put the sine of x here, the antiderivative is negative cosine, and the antiderivative is negative sine. We append these little pluses and minuses, and then we multiply, right? And we integrate. So doing all that, I get this original integral is equal to minus e to the 3x cosine of x, and then plus 3e to the 3x sine of x. Remember, we integrate going this way, so it's minus 9 of the original integrals e to the 3x sine x dx. Okay, so we take those 9, add them up to the 1 that's over here. That gives me 10 of the integrals. Is equal to minus e to the 3x cosine x plus 3e to the 3x sine x. So the integral by itself is 1/10 of this sum minus e to the 3x cosine of x plus 3e to the 3x sine x. Don't forget the constant. Okay, number 10. 1 is immediately integrable using a log rule. Well, that's this one. It should scream out at you. This is the natural log x squared plus 1. Hopefully you use parentheses, not absolute value. And the other requires some algebraic simplification. So we have 2x. If we look at this and I were to just say simplify that in algebra class, you would probably factor the x out, and you get x plus 1. And then you would cancel. And so we're integrating, bring the 2 out if you want. That's 2 log absolute x plus 1 plus the constant. Consider these. You can find antiderivatives for 3 of them. Integrate the 3 you can, and explain why one of them is not integrable using the techniques that you've learned so far. Okay, so looking at these, I guess this is probably the easiest one, right? You just put a 2 in and a 1/2, so we get 1/2 e to the 2x plus c. The next easiest one is probably this one, right? So what I would do is think of it as e to the x squared. I have an x dx. I want a 2x dx, so put a 2 and a 1/2. So this becomes 1/2 e to the x squared plus a constant. This one is sort of screaming parts. So let's do that one. Here's x, 1, 0, e to the 2x, 1/2 e to the 2x, 1/4 e to the 2x. Notice integrating this way, that's going to give us our constant. So plus minus, looks like we have x over 2 e to the 2x minus 1/4 e to the 2x plus a constant. This last one is the one that we cannot integrate. We would want to use this rule. Unfortunately, u is x squared, du is 2x dx, and we have the dx, but we don't have the x. We can put a 2 in, but it doesn't do us any good. You cannot introduce variables. We will actually integrate this one in April. It requires an infinite series to do. This is the one that was in your book, so hopefully you practiced it. And this is depth. This is light intensity. They tell you that at the surface, if the depth is 0, the intensity is something, you can call it L. At 18 feet later, the intensity is half of that. So 18 and then L over 2. Here's the exponential decay curve. We know it's exponential because the differential equation says derivative of L with respect to x is directly proportional to L. So let's find the equation of that line. L is going to be, well, remember this ordered pair is 0, L. It's sort of weird saying that we have an L that's a variable and L that's a number. Maybe if we wanted to be real technical, we can call that L sub 0, the initial, and this is half of that. If that bothers you, you could put a number here. Just put an arbitrary value in there like 8 and then call this 4. It all works out the same. You use 1 and 1/2. Okay, so here's my equation. 8 times 4 over 8 to the x over 18. Double check. If you put 0 in for x, you get 8. And if you put 18 in for x, you get 4. So this is the equation. Notice the parentheses reduces down. So we have 8. This is 1/2. And this is x over 18. Okay. Now, it says, how deep can you expect to work without artificial light? And that's supposed to be 1/10. So 1/10 of the surface value. So my surface value was 8. 1/10 of that is 8/10. Our task is to solve for x. So first of all, divide by 8. So we get 1/10. Take the log of both sides. I'll use natural logs. Natural log of 1/2 to the x over 18. And I use properties of logs, bring the exponent out front, divide through, so we get x over 18 is natural log of 1/10 divided by natural log of 1/2. And so x, the depth that we're looking for, is 18 times that. You don't need the calculator, but if you just wanted to check, you could do that pretty clearly. 18 times natural log of 1/10 divided by the natural log of a half. Okay, and that was the number that they gave you in the problem, 59.8 feet. Okay. Hopefully you worked that the day before, because that was one of the red problems that I said would be on the test. Okay, so slope field, we should spend about 15 minutes on this. The first thing to do is to sketch a field through these 12 points. Let me go over here. dy dx is x plus 1 over y. So notice that y is never 0, so we don't care about this axis. Y is not 0, so we're not going to consider that. If x is -1, then the slope would be 0. So that takes care of these 4. Whoops, sorry, if x is -1, then the slope is 0. So that's those guys. If x is 0, then dy dx becomes 1 over y. It's the reciprocal of the y coordinate. Well, 1 over 1 is 1. 1 over 2 is a half. 1 over -1 is -1. 1 over -2 is -1/2. And if x is 1, then dy dx becomes 2 over y. So 2 divided by the y coordinate. 2 divided by 2 is 1. These guys are sort of lined up here. 2 divided by -2 is -1. These guys are lined up. 2 divided by 1 is 2 divided by 1 is 2, so this is steep here. And 2 divided by -1 is -2, so that's steep there. So that would work. Okay, while the slope field in part A is drawn at only 12 points, it is defined at every point in the xy plane for which y is not 0. Describe all the points where the slope now is equal to a -1. Okay, so obviously this guy had a -1, this guy had a -1, and in fact any point on that line would have a slope of -1 except for this. So if I had to describe them, I would say all the points that fit, what is this? Y is equal to -x minus 1, with the restriction that x has got to be bigger than -1. So this would be a description. All the points on that line from -1 on out. Anything up here in this quadrant, those are going to be positive slopes. Okay. I say that, let me think. What would happen if we actually had -2 and 1? If that was our point, -2 and 1, and dy dx was x plus 1 over y. So at that point, we would have -2 plus 1 over 1, which is -1 again. So maybe we can go that way. There we go. Looks like we can keep going. So it's going to be all the points on that line, but x cannot equal -1, because then if x is -1 on that line, y is 0, and you can't divide by 0. Okay, so I like this answer better. I had to think about that for a little bit. Okay, part C. Same problem. So, yeah, solve the differential equation. So this is, I think if you look at the rubric, and I'll give you a link tomorrow you can look at, or maybe I'll email it to you. You get a point for, I think there were 6 points, maybe 5 points for solving this differential equation, 5 out of the 9. So dy dx is x plus 1 over y. We separate, so we get y dy is, x plus 1 over 1. So x plus 1 dx, that's the separate. Then we integrate. So we get y squared over 2 is x squared over 2 plus x plus a constant. At some point we got to do that. Maybe we can do it now. You could do it now, you can do it later. If x is 0, y is -2. So this becomes what? 4 over 2 is c. So c is 2. Let me chuck that in there. C is 2. So I've done most of the work here. The last point is just a little tedious. It does say you have to solve this for y. So we've done all the calculus at this stage. This is an equation. It's not explicitly an explicit equation of y in terms of x, but rather it's implicitly defined. So let's see if we can solve this. If we multiply by 2, we get x squared plus 2x plus 4. If we take the square root, now we got to be a little careful. Is it plus or minus? That's the one we have to look at. X squared plus 2x plus 4. I think nationwide a lot of people lost this. Y is in fact negative. We know that from the initial condition, so we have to choose the negative root. Okay, so the full solution to this one, there's the function that gives me the correct solution curve. Rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Now notice this is not logistics. Technically, it's not exponential either. It's more akin to that the heat equation, where you put, this is like the room temperature, and you put something here, and it goes like that. But we don't have to do that. We just have to answer some questions. The bird gaining weight when it's gaining weight faster, when it weighs 40, or when it weighs 70. So dB dt evaluated when b is equal to 40 is equal to 1/5 times 60. And dP dt, this is the rate the bird is gaining weight when the bird's weight is 20, is 1/5 times 80, right, which is 16. So if we put units here, these are grams per day. So this is 12 grams per day, and this is 16 grams per day. It's gaining weight faster when the bird is only 20 pounds. Okay. Find the second derivative in terms of b. This is sort of a hard problem, I think, but let's go ahead and find it, and then use that to explain why this does not look like it's logistics. This is not a logistics differential equation, but you have to reference the second derivative. So here's the first derivative. Derivative of b with respect to t is 1/5 times this, 100 minus b. I suppose if we wanted to multiply out, we could. We don't have to. 20 minus 1/5 of b. That's the first derivative. To get the second derivative, you just take the derivative of the first derivative. So the second derivative now is going to be the derivative of 20, which is 0, 1/5, and the derivative of b is dB dt. So we have the second derivative, but it says it's supposed to be in terms of b, which means we've got to get rid of this thing. Well, do we know what that is? Well, sure enough, we do. It's this. So again, and you're good. Here's the second derivative of b with respect to t. It's going to be 0 minus 1/5 times dB dt, which was 1/5, times 100 minus b. If I clean that up just a little bit, I get -1/25 times 100 minus b, or what's that, negative 4 plus b over 25. Right, that's the second derivative. We know that b is bigger than 20. B is bigger than 20. So this is negative 4, and this is going to be 20 or some other number. Let's see, how big can b get? Does it say what the maximum? Go back to the problem. Does it say how big the bird gets? The adult weight. Yeah, the bird is no more than 100 pounds. That's the difference between the adult weight and its current weight. So b has got to be less than or equal to 100. The worst case scenario is b, let's do it this way, 20 is less than b is less than 100. If b is equal to 100, then this becomes negative 4 plus 4. If b is anything less than 100, this is going to be less than 0. So I guess you sort of have to argue it that way. Again, a difficult problem, no doubt. The second derivative is negative. The second derivative is less than 0. So we have to have concave down. This is the problem here. It can't be concave up. However you wrote that. This one's a lot more straightforward. Find the particular solution, separate, integrate, figure out what c is. Okay, so separate db over 100 minus b is equal to 1/5 dt. Integrate, this is 1/5 t plus a constant. This one you would have to throw in a negative and a negative, right? To get, you can think of it now as negative 1, the integral of 1 over 100 minus b times negative 1 db. So this is a log, negative log. We don't need absolute values. We know the bird's weight is less than 100, so we can do it this way. And that's 1/5 t plus a constant. And so what could we do? Let's go ahead and figure out what the constant is here. Let's get rid of the minus sign. And I'll just call that C1. It's a different constant. And then we go ahead and exponentiate. So 100 minus b is e to the minus 1/5 t plus c2. We'll pull that guy out front. So 100 minus b is capital C, e to the minus t over 5. The initial condition was at 0, the bird weighed 20. So we put all that in there. We get 80 is equal to C e to the 0. So C is 80. Put that in there. And so if we, we're supposed to solve for B. So it looks like if we put the B on this side and then subtract off the 80 e to the minus t over 5, that should work. I don't know if the calculator was permitted on here or not. I don't think it was, but let's just go ahead and dump this in here anyway. 100, take away 80, e raised to the negative x over 5 power. For my window, I'll start with 0. I don't know how many days a bird lives. Let's say it lives just a couple months. We'll go every 7 days. How about that? Once a week. Starts with 0, and we know it goes up to 100. That's the max weight. We'll go by tens. And here's the graph. So sure enough, it looks like it achieves max weight pretty quickly. 60 days was too optimistic. Let's try 20 days. Okay, so that's the graph. They didn't ask us to do it, but that's the solution. For the bonus, how much time? Let me check my recording time here. We're at 30 minutes, so maybe you could have played with this if you did the other ones that quickly. What do we got? We got a differential equation. We got a second derivative. I don't know if we'll need that or not. That's that. Y, that's the solution to this guy. And we have an initial condition. So just looking at the points, this is equation of tangent line. That's pretty easy. This is use the tangent line. This is find the solution. So the vast majority of points are going to be down there. Let's go ahead and separate and integrate. So we get x dx and dy over y cubed. Let me do that as y to the negative 3 dy. X dx just makes it easier to integrate. So x squared over 2 plus a constant, y to the negative 2 over negative 2. Or if you want, x squared over 2 plus a constant, and this is negative 1/2, or negative 1 over 2y squared. Let me pause this. Okay, so let's use the initial condition, which was f of 1 is 2. So we get negative 1/8, right? Y is 2, and x is 1, 1/2 plus c. So c is negative 1/8 minus 4/8. C is negative 5/8. That goes back up into here. So I get negative 1 over 2y squared is x squared over 2 minus 5 over 8. I want to make this a proportion. 2y squared. So this is 4x squared minus 5 over 8. And again, we have to solve for y, so I'll flip this upside down. 2y squared over negative 1 is 8 over 4x squared minus 5. Ask me tomorrow about the upside downable theorem. It's a cute story. 2y squared is negative 8 over 4x squared minus 5. So divide that by 2, and we get y squared. It's negative 4 over 4x squared minus 5. So y is going to, again, we are going to have to look at the condition to see whether we want the positive root or the negative root. The initial condition, remember, y was positive. So we want the positive root here. So that would be full credit. That's the solution to the differential equation using the initial condition. Now, I'm pretty sure I can find the rubrics for all these things. I'll shoot them to you. Oh, we never did use part B. Use the tangent line. We never did write the tangent line. That's the easy one. Okay, tangent line. Y minus y1 n times x minus x1. So y minus 2, the slope is here. This is m. And the point we're using is 1, 2. So the slope is going to be 1 times 8. So that's 8x minus 1. Done. That's part A. That's this guy. Use the tangent line in part A to approximate. Okay, so we know that y, this now is the tangent line. y is 2 plus 8 times x minus 1. If I call that L, that's the tangent line. So maybe L of x, how about that? And f of x is about the same as L of x. So we're supposed to figure out an approximation for f of 1.1. That's going to be L of 1.1. And that's going to be, just put 1.1 into the L equation. So we get 2 plus 8 times 0.1, 2.8. So the last thing is explain why this is going to be bigger than or less than. So that sounds like a concavity thing. Is the tangent line below the curve, in which case the tangent line would be an underestimate, or is the tangent line over the curve, in which case the tangent line approximation would be an overestimate. So maybe knowing something about concavity, we could do that. We do have the second derivative. That's a concave thing. Let's see, the concavity evaluated at 1, 2 is going to be equal to 8 times 1 plus 3 times 1 times 4, 3 times 4, 8 times 13, which is bigger than 0, positive. So at the point of tangency, we know we're going to be concave up. And we're near the point of tangency, we're over here. My gut instinct is it's going to be an underestimate, less than. I think for full explanation, we would have to do an infinite series. But let me stop this here. Again, we'll pull up the rubric and look at it together in class. So I'm at 37 minutes. You had 49 minutes to play with this. You didn't have to do the bonus. Okay, so stop.